You know the scene. Your cat is sitting perfectly still in the middle of the room, pupils slightly dilated, completely locked onto an empty corner or a blank wall. No sound, no movement. It is a running joke that they are staring at a ghost. But the biological reality is far more interesting. That cat is actively processing a massive stream of complex sensory data. Humans live in a tight, low-bandwidth sensory bubble, missing almost everything happening around us. A cat's body is a highly evolved piece of surveillance hardware designed to capture the signals we miss. To understand this intense fixation, we have to reverse engineer their biological hardware, starting with their audio receivers. When a cat stares at nothing, they're actually interacting with a rich, invisible world of physical data that our senses simply cannot access. Look at a cat's outer ear, known as the pinnae. These function as independently rotating satellite dishes, powered by 32 distinct muscles that allow for 180 degrees of rotation. The physical cone shape of the pinnae catches and naturally amplifies incoming sound waves by 2 to 3 times for specific frequencies. This chart compares our hearing range to theirs. It plots the maximum hearing ceiling of an adult human at 20,000 Hz, alongside a cat's extended range, which reaches a staggering 64,000 Hz. That is a massive ultrasonic bandwidth. In that ultrasonic range, a cat easily detects the high-frequency echolocation pulses of bats outside, or the microscopic squeaks of rodents hidden deep inside your drywall. The system's targeting accuracy is razor-sharp. From 3 feet away, a cat can pinpoint the exact origin of a sound, distinguishing between 2 sources just 3 inches apart in 0.06 seconds. A cat staring blankly at a silent wall is likely achieving an acoustic lock on a target moving just beyond the threshold of human hearing. Their optical sensors match this precision. A cat's eyes contain a high concentration of rod cells, acting as low-light motion detectors, backed by the tapetum lucidum. This reflective layer of tissue behind the retina bounces light back through the eye to boost night vision. This hardware allows them to see imperceptible movements, tracking dust motes riding thermal air currents or the rapid refresh rate flicker of a digital screen. All of this raw sensory input is fed into specialized tracking software in the brain, a neural pathway known as the ascending tectofugal system. Red arrows trace the ascending tectofugal pathway, bypassing primary visual cortex A17. Routing data directly to the superior colliculus and lateral medial suprageniculate nuclei discards object identification. The brain stops calculating what things are, acting purely as a motion detector determining location. This graph illustrates exactly how these tracking neurons react. Look at the velocity response curves in graph B. They show a massive spike in the neuron's discharge rate at extremely high